Okay, good morning, welcome back. Today is September the 12th. We're doing class 3, something about limits and continuity today. Still working on the two projects, arbitration and trucks. Our very first quiz is still a little ways away, September 23rd. We'll talk more about the quiz as we get closer. Questions on the calendar? Okay, one quick announcement. 4. Yeah, okay. All right, so here at the top of page 21, in this class we calculate limits and discuss the concept of continuity. Limits are at the heart of finding slopes of tangent lines, which is a fundamental process in Calculus 1. Remember we talked about slopes of tangent lines last class with our zombie race. Just a quick refresher, what did the slope of the tangent line represent for those zombies? How fast they were going instantaneous, right? Not the average velocity, but the instantaneous velocity. Super. Okay, number 1 says we're going to find the value of this particular limit. So it's a limit as x approaches 0 of the fraction x over the square root of x plus 1 minus 1. So it's our first formal limit. The idea here is we want to know what happens to the value of this fraction as x gets closer and closer to 0 in this case, because we got the x arrow 0. So we want x to get closer and closer to 0. And so we're going to do this in several different ways. First step, whenever we're faced with a new limit, is to just try plugging in. In this case, x is approaching 0. How about we just naively plug in x equals 0 and see what we get? So what do we get on top when x is 0? We get 0, and on the bottom, I'll write it out, and then we'll do the calculation. But again, just substituting, do we get -1? We get 0 on the bottom as well, right? So 0 on top, 0 on the bottom. It's a mess. What this means to us is that we have more work to do. But the very first thing you should always do when you see a new limit is just plug the thing in. And if you get something that's reasonable, which that is not, then you're done. If you just get an ordinary number, you found the answer. The most important limits that we'll see this semester will be fractions, where you appear to get 0 in both the numerator and the denominator when you plug in. The preceding is an example of what is called an indeterminate form of type 0 over 0. Indeterminate means it hasn't been determined yet. The answer could be anything. The answer could be 5, it could be -12, it could be infinity, it could be 0, it could be anything. It is not determined just yet. When we get 0 over 0, it means there's more work, algebra, to be done, but we'll try 2 other techniques before we do the algebra. So part B is looking at a graph. So here are some screenshots. Let's interpret the screenshots. In the first screen here, we see that y1 has been replaced by, or I typed in our function right here into y1. And then there's the window. We'll come back to that in just a second. But here's the graph on the far right. And what we're interested in, again, is a limit as x approaches 0. And so x approaching 0 is on the x-axis. And we're going to approach 0 from numbers bigger than 0. And we're also going to approach 0 from numbers smaller than 0. Let's do 2 different colors here, like that, okay? And the question is, what is happening to the function? But remember the function, this thing right here, we typed in for y1. So really what we're after is what's happening to the y values on that curve when you approach 0 on the green and when you approach 0 on the purple. And as we approach 0 from the right-hand side, the y values are heading towards, let's say, that number right there. And as we approach 0 from the left-hand side, the y values are heading to the same number, whatever that number is. And to find that number, we'll just take a quick look at our window. The y min and max are 0 and 5, and the scale is 1. That means every hash mark you see on the y-axis is 1 unit apart. So what do you think? What number is that blue? Looks like 2, just by counting hash marks. And so our estimate, I'll just write it here and maybe copy it just so we can start getting in the habit of using the good limit notation. So the limit as x approaches 0 of the function. And so we type that whole function out. Is it a standard form to do x approaching 0? Yeah, in some books I've seen stuff like this, like if they don't really have the ability to typeset it off, but much easier I think to read is the x below. Okay, this limit is equal to, all right, so what did we think the y values were approaching? 2. That's what we say the limit is. The limit is 2. Now that's kind of funny because up above, when we just plugged in, what did we get for our fraction? 0 over 0, which is not defined. It's this wacky kind of thing. And apparently it's approaching 2 in this case. If we were to zoom in on this area right here, like really zoom in and get that y-axis out of the way, do you know what we would see at that one point? We would see a hole. The fraction is not defined at x equals 0. You can't divide by 0 no matter what. There's going to be a hole right there. But the limit doesn't really care what's happening at the point x equals 0. The limit just cares what's happening nearby. And nearby, we have this really nice behavior, both sides approaching 2, even though there's a hole just at that one moment in time, okay? All right, so that is estimating a limit by looking at the picture. And in part C, we can also estimate a limit by, looking at a table of values. So y1 is the same. It's the same formula still typed in there. Then we've got this thing called table setup. And I just want to highlight that I have set the independent variable to ask. And what that means is that if I go into the table screen, which I think is right above graph on the TI 83 and 84, I get to type in whatever numbers I want right here, as opposed to the calculator generating a list, you know, x is 1, x is 2, x is 3, x is 4. I type numbers in. What kind of numbers did I type in here? Very little, very close to what number? 0. And I didn't just pick numbers that were positive, I also picked some numbers that were negative. And the key here is you want to approach 0 from both sides. I'm supposed to remind you of this green and purple thing that we just did up above, both sides. And I also plugged 0 in right in the middle. What happened when I plugged 0 in the middle? I got an error. You still can't plug 0 in, even with the big, fancy, expensive calculator. We can't plug 0 in, but we can plug in numbers really close to 0, like 0.1 and 0.01 and 0.001. And let's see, if I'm coloring here, the numbers at the top, the negative 0.1, negative 0.01, is that purple or green? Those are the purple numbers. And so as we approach from numbers less than 0, what does it appear that our numbers are heading towards? Looks like 2. And in green, as we approach 0 from the right-hand side, what does it look like our numbers are approaching? Again, 2. And so looking at a table of values, more compelling evidence that in fact the limit is 2. Okay. That said, can you look at that graph and definitively say the limit is 2? Do you know for sure it's exactly 2? Couldn't it have been 2.1 or 1.98? Yeah.
Because you can tell it's 2 because 0.001.
Yeah, there's more evidence there. There's this nice symmetry, right? And so like if the answer is someplace between 1.995 and 2.005, I'm probably going to guess 2 every day of the week. But isn't it possible that at some point in there something funky happens and really the answer is 2.0007, right? It's possible. And so these are just pieces of evidence, but there's no proof here. These are just guesses. Well-reasoned guesses, but guesses. So part D here is the sort of be-all, end-all. If you really want to know for sure with 100% certainty what the limit is, you got to do some algebra. So let's do some algebra here. We are going to, again, copy the original with good limit notation. X over square root x plus 1 minus 1. And then we're going to do some algebra. And there's a technique from your algebra or pre-calculus past where somebody told you how to get rid of a radical in the denominator. Anybody remember the fancy name for that technique? It wasn't about reciprocals. This one, the name that I've heard is rationalizing the denominator. I heard that before. And so here's the idea. We are going to multiply the bottom of this fraction by a certain thing. Looking at the square root of x plus 1 minus 1, we're going to multiply by a very particular thing. Anybody know what that is? What is it? The conjugate. It's perfect. What is the conjugate? Square root x plus 1 plus 1. Very subtle but important difference is changing the minus sign between the two terms to a plus sign. That's the only change you want to make. But you can't go around randomly multiplying the bottom of a fraction by something without also multiplying the top by the same exact thing. So at this moment, we put a copy upstairs. Multiply top and bottom by the same thing. That's legal. Equals. The next symbol you have to write after this equal sign is LIM. Okay, upstairs we're just doing a lot of copying. X, and then I'll put parentheses, square root x plus 1 plus 1. But downstairs is where the magic happens. Okay, so we're going to do 4 multiplications here. When we do the first times the first, what do we get? X plus 1, right? Radical x plus 1 times itself is just x plus 1. That's lovely right there, x plus 1. When we do the outer terms, we get 1 radical x plus 1, right? Inner terms, negative 1 radical x plus 1. And when we add them together, they cancel. That's the idea of the conjugate. So we're not going to write either of those, but the outers and inners just poof, disappear. And then finally, the last, minus 1 times plus 1 is minus 1. Okay, and just to save a tiny bit of space here, what do we get on the bottom? We'll do a couple of steps in one here. On the bottom, we just get x. And then what can we do with that x on the bottom? We can cancel it with that x sitting in the front. So I'm going to cross all of this off with that x right there. Equals limit as x approaches 0. So all that we have left is what's in the numerator there, root x plus 1 plus 1. The denominator all canceled, so there's an invisible 1 in the denominator. And that right there is just a brand new limit. And way at the top of this page, I said the first thing you should try when you see a brand new limit is plug it in. Plug in whatever the number is. It's 0 here. It's not always 0, but you got to plug in when you see a new limit. And let's see what we get. When we plug 0 in, equals square root of 0 plus 1 plus 1, right? And that's a perfectly good number. What number is that? 2. Hey, it's 2. And now there's no doubt the limit is, in fact, 2. Questions on the algebra? Yeah, Nick.
The x plus 1 minus 1. Technically doing the 1 minus 1 curve, right?
Yeah, that was me being really lazy. So let's put that again. X plus 1 minus 1. Okay, so the so the plus 1 and the minus 1 cancel with each other. And then the x cancels with the x. Yeah. Other questions? Okay, just one piece of notation, and you will find that I am a stickler for notation, is that the limit appears every place until we actually do the plugging in. And that at that one moment where you change the x to a 0 is where you stop writing limit, okay?
So your final answer is 2.
Final answer is 2, and we also didn't write limit here, which was the step where we plugged in the x, plugged in 0 for the x. And I know it's kind of annoying to lose a point here and there because of like bad notation and not writing limits and things. But, you know, imagine you were in an English class and you just didn't capitalize the first letter of sentences. That's not so great, right? And if you just decided, you know, I'm not going to use any punctuation in this paragraph, you'd expect to lose some points, right? So that kind of notation is the mathematician's punctuation. And if you don't include it, it's just not right. Like if you don't put periods at the end of your sentences, it's just not right. And the person reading probably could still figure out what you're saying even without all those periods, but it's not right. Okay, the activity is on the next page. Let's just run through the directions real quick, and then we'll read my strong recommendation, which is not on your paper. So there are 5 limits down below here, A through E. And it says for each limit, you're going to investigate the limit by looking at a graph. That means you're going to be typing into a graphing calculator or an app on your phone or your computer. And I do have actually got a good number of graphing calculators to loan out today for people that don't have one on them. But you're going to make the graph on the calculator and draw just a real rough sketch from your calculator. You're going to investigate the limit by looking at a table of values, again, on the calculator, and then you'll write out a few of the values on your paper, and then you'll make a conjecture about the value of the limit. There are a couple of them in here where I'll also ask you to do the algebra, but don't do the algebra unless it says it. Now, the calculator stuff is not hard, but it is time consuming and the activity is long. So what I really want us to do, this is my strong recommendation that is not on your packet, is to divvy up the calculator work. So for example, each person will make a graph and a table of values for one of the 5 parts, A, B, C, D, E, and then you do your answers and then just pass these calculators around the table, okay? So we're not doing a lot of mindless typing in, right? So just pick one or maybe 2 if you're really quick with the calculator, and we'll pass them around. Okay, so let's see how far we can get. The activity goes for several pages. The goal is to get all the way through the end. I'll walk around and loan some calculators.